All right, I just back in the office after lunch and one faculty meeting. And in this video, I'd like to finish the previous week lecture slide. And we are left with one topic that is about existence of Walrasian equilibrium. So chapter 17 in Musgrave Winston Green is concerned about the positive theory of equilibrium. We attempt to describe the real world with an economic model. We would like to describe people's behavior with an economic model. We would like to find out equilibrium and to see whether model's prediction and model's equilibrium is consistent with people's behavior in the real world. Whenever we do such a positive theory analysis, the very first thing we have to do is to check the existence, whether equilibrium does exist or not. If the equilibrium does not exist, it completely nullifies our analysis, the whole analysis. And there's no way to justify our equilibrium analysis if it turns out that equilibrium does not exist. Yeah, so although existence problem sounds tedious, it is in fact very important and fundamental question in economic theory. So if some economists prove their existence in an important class of games or models, it guarantees publication in top journals. That is what equilibrium or existence problem is. So in this video, we are going to examine under what conditions does the general equilibrium model possess a solution for equilibrium. Right? And Musgrave Winston Green provides us a very long and complicated and delicate proof for the existence result in general framework. But we'd like to make our life easier, right? So in order to simplify analysis, I'm going to narrow down the scope to the pure exchange economy model. So we abstract away the production process. We just look at exchange economy model where several consumers created their initial endowment. And in the model, we are going to establish the existence of equilibrium using the excess demand function and its several properties we established in the previous lecture video. All right, so the starting point is proposition 3.1. So let me go back to 3.1. It tells us in exchange economy where preference relation is strictly convex and locally non-satiated, and price factor P is going to be Walrasian equilibrium price factor if and only if excess demand function takes a non-positive value. So using this theorem, we can restate the existence question like this. Is there any price factor P at which the excess demand function takes a non-positive value? And this statement is under the assumption that preference relation is locally non-satiated. If we strengthen that assumption to strong monotonicity, so whenever preference relation is strongly monotone, and this inequality becomes equality, so now the existence problem can be stated as follows. Is there any price factor P solving this system of equations? Okay? If the answer is yes, then we prove the existence. So this is why proposition 3.1 is useful. It's especially useful when we examine the existence issue of equilibrium. All right, so going back to slide number 24, using proposition 3.1, existence problem can be put as follows. Any price factor P satisfying Z of P is lower than equal to 0, or under the assumption of a strong monotonicity, any price vector P solving this system of equations. Okay? So let me first examine existence problem in 2x2 model. So there are just two consumers and two goods. It does not necessarily that it's not necessary that there are only two consumers, but two goods. This assumption is important. So in case of two goods, we can easily establish the existence of equilibrium by taking the following steps. Because there are only two goods, excess demand function has just two functions, Z1 and Z2. Demand for good 1, excess demand for good 1, and excess demand for good 2. But because there are two goods, price vector is also two-dimensional vector, P1 and P2. So, under the assumption of strong monotonicity, we have to figure out whether there exists a price vector P1 and P2 at which this function boils down to 0 and 0, the 0 vector. So at such a price P, Z1 is equal to 0 and Z2 is equal to 0. Right? So now we encounter system of simultaneous equations. Okay? But by Wallace law, we know that at some price vector Z1 is 0 and Z2 is automatically 0. And so Wallace law allows us to work with one of these two functions. Although we have a simultaneous equations, we don't have to think about the other equation. We can just work with one equation. That is enough. So now we are looking for now we examine whether this function z1 has a solution. So this equation has a solution or not. Is there any price vector p1 and p2 at which this z1 function is going to be 0? All right, and then so Wallace law simplifies the problem into, so Wallace law enables us to work with just the one equation among these two. And I'm going to use the first property of excess demand function. So we know function is homogeneous of degree 0. So originally z1 depends on two variables, p1 and p2. But because z1 is homogeneous of degree 0, so we can divide this price vector by p2, p2 and p2. So can normalize the price of a good 2 to 1. So p1 over p2, price of a good 1, after normalization, becomes a p1 prime for say, but with a slight abuse of notation, let me call this just a p1. So using the fact that function is homogeneous of degree 0, we can simplify this function further. Originally, it depends on two variables. So it is a function with two variables. Now we can work with one function with a single variable. All right, so we can draw the graph of this function on the standard Cartesian plane. So putting P1 on the horizontal axis and excess demand function on the vertical axis, we can draw the graph of this function. All right, so here's one possible example. Now let me use the third and fourth properties of excess demand function. Excess demand is defined as aggregate demand for good 1, so x1, minus initial endowment of good 1. Now this is independent of p, okay, it's an initial endowment, but x1 depends on price, p1. So if p1 is very close to 0, as price 1, so price of good 1 approaches 0, right? And what happens? The demand, we can easily anticipate the demand for the good diverges to positive infinity. This demand will be very high. Yeah? So we'll dominate this initial value, initial endowment. So Z1 will go to, so it will tend to positive infinity, right? And if P1 is sufficiently high, then it will reduce the demand for that good. So X1 will be very close to 0. So as long as omega 1 is a positive. So as long as omega 1 is strictly positive, excess demand function takes a negative value. So by using the third and fourth properties of excess demand function, we know when P1 approaches 0, Z1 goes to positive infinity. But if P1 is sufficiently high, there is no upper bound for P1. But if P1 is sufficiently high, this excess demand function goes below the horizontal axis. Okay? And then now finally, let me use the one more property. So in the first step is a first property of excess demand function, continuity. So we know excess demand function is continuous in price. And at low price, Z1 takes a positive value. Sufficiently high price, Z1 takes a negative value. And Z1 is continuous. So there must be at least one price, P1 star, as is displayed in this figure. At this price, Z1 is equal to 0. Because it is a continuous function, so the graph must be continuous. We have a positive value at low price, negative value at high price. So there must be at some point at which the function will pass through the horizontal axis. So there is a solution, P1 star, to this equation. Okay? So that is the way to prove existence in case of Tugus. So the existence formally follows by the intermediate value theorem. Okay? Now the thing is, the problem is, unfortunately, this proof is only applicable to two good case. There's no way to extend this theorem to, several good case. Okay? So when there are more than two goods, excuse me, we have to employ the following theorem, the so-called Brouwer's fixed point theorem. Okay? And this theorem tells us if we have function g, and that is continuous, and it is defined on space A, and space A is a non-empty, compact, and convex subset in the Euclidean space. And it is a continuous mapping from space A to itself. Okay? So it is a mapping from space A to itself. And the space A should be non-empty. That is easy to verify, but it should be compact, bounded and closed, and convex set in the Euclidean space. Then the theorem tells us there exists a point x star in the space A, so in the domain, such that g of g function takes the same value as the argument at that point. So g of x star is the same as x star. So at this point, at which g function takes the same value as the argument is called the fixed point of function g. All right? And I'm not going to prove this statement, this mathematical theorem in this video. If you're curious about the exact proof, you may refer to Mathematical Appendix in Moscow and Winston Green, or you may refer to other mathematical econ textbook, say Simon and Bloom's textbook. But I can illustrate the basic idea of this fixed point theorem with a simple figure. Okay? So think about a one function g defined on unit interval. So here is a unit interval 0 and 1. And once again, this function g is defined, if this function g is defined on unit interval, then codomain should be unit interval as well. Okay? So codomain must be unit interval as well. So inside this unit square, we can imagine one continuous function. Before drawing the graph of the function, let me first draw the 45-degree line, y equals x. Okay. Now let me draw a one continuous function inside this box. Remember, the codomain is also 0 and 1, so this graph can go outside this unit square. It must be in this unit square. Okay, then what happens? This graph must have some intersection with the 45-degree line. Okay? And at this intersection, we have a fixed point because, let me call the x coordinate of this point x star, and y coordinate is also x star because this is on the 45-degree line, and this is on the graph of the function. So g of x star is also same as x star. So by definition of fixed point, x star becomes a fixed point of function g. Okay? So that is the basic idea behind this theorem. When domain is compact and non-empty and convex set, unit interval is a compact and convex subset. And function is continuous defined on this unit interval. And codomain is also unit interval. All right? Then the function g must have a fixed point, at least one fixed point in the domain. And most existence theorems in economics rely on this kind of fixed point theorem. So, for example, if you studied game theory or advanced game theory, you may have seen John Nash original proof about the existence in finite games. So when there are finite number of players, and each player can choose one of a finite actions. So the games are finite people and finite actions. And John Nash in 1950 proved that, so he has proven that such a finite game has an equilibrium. So since then, we call that equilibrium of a game Nash equilibrium, named after him. So he used a one fixed point theorem in that proof, in his original proof, the so-called Kakutani's fixed point theorem, because in finite games, player's best response is not necessarily a function. It might be a correspondence. So Kakutani's fixed point theorem is about the correspondence, and Brouwer's fixed point theorem is about the function, continuous function, right? So John Nash adopted a Kakutani's fixed point theorem to establish existence. So since then, every economist is aware of got to know the Kakutani's fixed point. So most existence theorems in economics depend on such a the most existent theorem in economics have been established by with the aid of this kind of mathematical fixed point theorem. All right, and then here is the statement that we are going to prove in the remaining time. So that is a existence in pure exchange economy. So consider pure exchange economy where preference relation is continuous. So utility function is continuous and strictly convex. So demand function, so demand is not correspondence, is a function. And preference relation is locally non-satiated. All right, and then initial endowment vector is strictly positive. So every commodity has some positive units at the outset. All right, and the theorem states that there exists at least one price vector P star such that excess demand function is a non-negative or non-positive at this price vector. So by proposition 3.1, we know that this is a equilibrium price. Yeah, so that is a existence. So now I'm going to prove this because this is a graduate course. I never tried to prove some existence problem in any classes I've taught so far, but this is a graduate course for microeconomics. I think it is instructive it is instructive to see at least one time in your lifetime uh, how do you prove existence in some models, because you never know. You have to prove, you have to go through this kind of proof when you do research in the future, or when you write down dissertation in the future. Yeah. So it is a little long, but it is instructive. Okay. So this is a how existence proof goes away. This is a how existence proof goes. Okay. So just as in 2 by 2 case, so here's a 2 by 2 case. Uh, in the second step, using homogeneity of degree 0 property, we normalize price factor, right? And then we start from, so we begin by normalizing price factor here as well. But in this case, so when there are more than two goods, we do not normalize the price of one good to 1. Instead, what we are going to do, first we are going to compute the sum of prices. Okay? So here, the sum of piece of k for all over the goods. So for over all goods, from k equals 1 to L. So let me call this price P. This is the sum of prices. All right. And then, because a excess demand function for each commodity k is homogeneous of degree 0, so we can normalize each price by dividing by this aggregate price. So P1 becomes P1 over P. So we divide each price by P. Still, ZK does not vary because it is a homogeneous of degree 0. All right, and what is the purpose of this normalization? What is this normalization for? Because we would like to use this Brouwer's fixed point theorem. But in order to apply this theorem, the space must be compact. It's bounded and closed. Okay? But price vector, the price vector can take any value. It starts from 0, but it can go to positive infinity. There is no upper bound. So this space is a not bound space. Right? So in order to make a compact space, we need this process of normalization. So now what happens? After normalization, now the space of price, so the entire space of price factors is going to be unisimplex. So to understand this, now we start from two good case. So in case of two goods, we have P1 and P2. Okay? Once again, each price has a no upper bound. It may go to positive infinity. But after normalization, so dividing by the sum of prices, each price is a number between 0 and 1, and their sum is equal to 1. In case of three goods, P1 plus P2 plus P3. Okay? After normalization, now we divide each price by the sum of prices, and P1, P2, P3 is a number between 0 and 1, and their sum is equal to 1. Okay, so in case of two goods, two variables, so the sum of the two variables equal to 1. That is this line segment, P1, P2. So that corresponds to this line segment. in case of two goose. In case of three goose, that's going to be this side, this plane. So one side of this tetrahedron. So in case of two goose, we have one interval that is a single dimensional space. In case of three goose, we have one plane that is a two-dimensional space. In case of L goose, after this normalization, the space of a price vector becomes L minus one dimensional unit simplex, which is compact. This simplex is non-empty. Clearly, this is non-empty and compact, now closed and bounded, and convex. If we choose any 2 points in this plane, on this plane, its line segment, linear combination, still lies in the set, the convex. So it satisfies all of the conditions for the space A, non-empty, compact, and convex. All right, that is this is the main purpose of this normalization. All right, now we define one auxiliary function, g sub k. So for each commodity k, we define g sub k as, so it is a function of a price. So it is a rational function. So on the top, we have a p sub k plus maximum between 0 and z sub k. Right? So this maximum, so maximum a and b. I think you have seen this maximum operator. So that is going to be a, if a is larger than b, and that's going to be now if b is larger than a. So it gives us some higher value between these two elements. So if z sub k is a positive, this maximum operator gives us a function, excess demand function. If z sub k is a negative, it boils down to 0. All right, and then the law of this maximum operator will be clear at the end of the proof. So we have this on the top. On the bottom, we have 1 plus summation of these maximum operators over every commodity. So because we have L commodities, and we add up these maximum operators from 1 to L. Okay? So now the denominator is independent of K. It's some number. Only numerator depends on K. Okay? Because we have L goose, we can define this function for each K. So G of P is a L tuple vector, G sub 1. Now G sub 1 is a P sub 1 plus maximum between 0 and Z sub 1 divided by this quantity, and this quantity applies to every function because it is independent of K. All right, so G of P is defined this way. We have L tuple vector. Now the thing is, first, G is a continuous function because Z, excess demand function, is continuous, and this is a rational function. So we have to check the denominator is equal to 0. And so this G function, auxiliary function G, is going to be continuous except where denominator is equal to 0. But denominator is 1 plus maximum between 0 and function G, or function Z. So no matter what this function, excess function Z, it is a larger than 1. So there's no chance that denominator is equal to 0. So this rational function G sub K is continuous everywhere. Okay? And then it is defined on P, so price vector, but we normalize price vector to unit simplex. So domain is non-empty, compact, and convex. And furthermore, this function's codomain is also unit simplex. All right, because function G sub K is defined by P sub K plus maximum of 0 and z sub k, and we have 1 and summation of maximum on the bottom, all right? Because p sub k is a number between 0 and 1 after normalization. P sub k is 0 and 1, between 0 and 1. And we have a summation of a maximum on the bottom and just one maximum on the top. So comparing the numerator and denominator, we can easily see that numerator is always smaller than denominator. And both are strictly positive. So g sub k is going to be number, its function's value, no matter what price vector p, it is a number between 0 and 1. And moreover, summation of g sub k, now we add this function over k. K goes from 1 to L. All right, then because denominator is independent of k, so we can pull it out and put it in front. So 1 over 1 plus summation of max, 0 and z sub L. Now we apply summation to the numerator, and we have summation of p sub k and summation of maximum. And this is 1. Yeah? That's the way we normalized. So these two are cancelled, and we have a summation of maximum. Yeah? So the numerator and denominator are equal to each other. So the summation of g sub k is going to be 1. So function g of p, that is an n-tuple vector. Yeah? Every element, every function is between 0 and 1, and summation of these all functions from 1 to all the way to L is also equal to 1. So codomain is also unisimplex. Just like P, every p sub k is a number between 0 and 1 after normalization, and the summation of p sub k is equal to 1. Likewise, g sub k between 0 and 1, summation is equal to 1. So function g is a continuous mapping from the unisimplex to itself. So it satisfies all the assumptions in Brouwer's fixed point. So we know that function g has a fixed point. Right? So this function has a fixed point. So there exists a p star such that g of p star is equal to p star. So this function has a fixed point. It is equal to, at price vector p star, it is equal to p star, p1 star, p2 star, pl star. So these two vectors are equal to each other, meaning that each component is equal to each other. G sub 1 at this p star is equal to p1 star. G sub 2 is equal to p2 star at this price vector, and so on. So we have these k equations. G sub k is equal to p sub k star at this price vector. All right, and now we demonstrate this price vector p is a Walrasian equilibrium price vector. Right? This is how we prove existence. Right? We found a fixed point, existence of fixed point, and the fixed point of function g becomes a Walrasian equilibrium. So now we are going to prove that this price vector p satisfies, so every excess demand function is going to be non-positive. This is a typo. Non-positive for every k. So by proposition 3.1, several typos in this slide. I'm sorry about that. But from proposition 3.1, we know that this p star, if a excess demand function is non-positive for every k, We know that P star is a Walrasian equilibrium. All right. So what I'm gonna do, so from equation number 2, G sub k is P sub k plus max G sub k over 1 plus summation max between 0 and Z sub L. So using definition of G sub k, I can rewrite the equation number 2 as this. All right? And then multiplying both sides by this. Okay, so moving this numerator to the right-hand side. And if you rearrange the equation, you will get this. You will get this. Because a P sub k will be cancelled from both sides. So we have this. And then now we multiply both sides by G sub k. Multiplying Z sub k here and here. And then we take the summation over k. Okay? Then the right-hand side, the expression on the right-hand side becomes this. And the left-hand side, we have a 1 summation in front over k. So Z sub k times P sub k, that is right here. And another summation over L in the second. Okay, and then because k and L are totally separable, so in order to compute this summation, we can separate this one and compute each summation. But the first summation is summation of P sub k times Z sub k. That is a dot product between price vector P star and excess demand function. So this one is P star dot Z of P star. And by Wallace law, that boils down to 0. Because Wallace law tells us no matter what the price P, the dot product and excess demand function at that price vector always is equal to 0. Okay, so this expression boils down to 0 by Wallace law. So we have this. Okay, now let me illustrate why we need this maximum operator. So this equation requires the sum of these components should be equal to 0. Okay? But if we ponder each term of this summation, each term of this sum is either 0 when, if Z sub k is a negative, then this maximum operator gives us a 0. So their product is going to be 0. So whenever Z sub k is a negative, each term is going to be 0. And if Z sub k is a positive, then we have Z sub k times Z sub k, because this maximum becomes a Z sub k. So we have Z sub k squared. That is also non-negative, no matter what Z sub k. So this sum is a summation of non-negative numbers, right? Because each component, each term is a non-negative number. It's a summation of L non-negative numbers, but the equation 3 requires this sum be equal to 0, right? So that means, so if any term were strictly greater than 0, so if Z sub k is a strictly positive, then we have a strictly positive term for some k. So there's no chance that we can satisfy this equation. That means each term should be equal to 0. So Z sub k must be non-positive for every k. So that proves the existence of equilibrium. Alright, so the proof is a little bit long, although I simplified a lot. But once again, I think it is instructive to see at least once um, the how to prove existence in economics using fixed point theorem, right? So you don't have to remember the proof, I mean, but if you understand each process of the proof, that might be instructive. Yeah? That strengthens your understanding about economic theory, and that also enhances your mathematical or economic knowledge. So we start with a normalization, and you may have to understand why. So you may have to think about why this normalization is necessary, what this normalization is for. Okay? But this is for getting a domain as a non-empty, compact, and convex set. So it turns out that after this normalization, domain is going to be unisimplex. And it's very difficult to come up with this kind of auxiliary function, but if we have this function, it's a continuous mapping from the unisimplex to itself, and so we can apply the Brouwer's fixed point theorem to obtain a one fixed point. And it turns out that this fixed point of the function g is a equilibrium price. That is how this equilibrium proof goes. So this is the end of lecture slide 3, and hope you guys enjoyed this video. And what I'm gonna do, I'm gonna make a one supplementary slide for the remaining topics in chapter 17, uniqueness and stability. And let me try record lecture videos maybe tonight or tomorrow night. Okay? And see you guys in the next.